Welcome to lecture 16 on RSA encryption. And first of all, disclaimer, this is not a high-level lecture on RSA encryption. It's just the basic idea of it, okay? But one of the principal things that we need to talk about in order to properly implement even my toy examples of it is what's called binary exponentiation. And so the idea here is to calculate a to the power m, all right, where maybe m is kind of big. It's helpful to write m as a sum of powers of 2. So of course you got your 1, 2, 4, 8, 16, 32, 64, 168, 256, 512, 1024, and so forth. So what you do with your number is you look for the largest one of these that fits into it, and then it turns out, of course, that you can write any number as a sum of these guys. All right. Sometimes you take 0 in that list, sometimes you take one of them, either 0 or 1. All right. So you can look at this in terms of the binary exponent of m, the binary expansion, like zeros and ones of m, but I've chosen not to do that as I think it's a distraction here. So anyway, this is called binary exponentiation. Let me give you an example. So, all right, here's an example of the idea. So to calculate 797, excuse me, mod 10, what we do, right, is first of all break down 590. I changed my mind on the number mid-calculation. I see it didn't make it to here. 597, there we go. So 597, excuse me. So we got 512 plus 64 plus 16 plus 4 plus 1. Let's see here, let me double check that. 64 plus 16 is 80. 80 plus 512 is 592. Plus 4 is 596. 597. All right, there we go. So notice that we calculate, so all these calculations are mod 10, right? So you've got 7 squared is 49, which is 9, is congruent to 9 mod 10. 7 to the 4th then is 7 squared squared, which is 9 squared, right? Which is 1. Oh, well, this is actually kind of not, this example is a little bit too easy actually, because you find out that 7 has order 4, so you could just use that to basically get rid of the rest. I mean, so this is a somewhat silly example. This doesn't usually happen. You don't usually get 1 at like the 4th power or something. That's kind of special, isn't it? And anyway, so 7 to the 597 is 7 to the 512 plus 64 plus 16 plus 4 plus 1, which means we can multiply these guys, right? But as we just calculated above, everything here is 1, 1, 1, 1, 1, except for the last 7, so this is just congruent to 7. So this example is almost too easy. Let me show you an example that's got a little bit more to it. So let's see here. 137 to the 281 power is what? Mod 100. This time I'll do mod 100. So all are mod 100. And then the reason I'm doing mod 10 and mod 100 here is mostly just to keep it simple to think through. Like in practice, the modulus we're working with in an RSA encryption calculation is uglier. But anyway, here it is. Just to get us the idea of binary exponentiation, here's an example. So first of all, I take 281 and break it down into powers, sums of powers of 2. So you can fit a 256 into that, a 16, an 8, and a 1. All right. And so then I just go about calculating all the way up to the 256th power of 137, mod 100. So 137 squared is, it turns out with my calculator, 18,769, which is of course congruent to 69. 137 to the 4th power is 69, is congruent to 69 squared. So I'm using this to replace 137 squared. Alright, so then it's squared. And then that 4761, which is congruent to 61. Then the 8th power, I take the previous one, I square it. That gives me 3721, congruent to 21. Then to 16th power, I take the previous one, I square it, that's congruent. That's equal to 441, which is congruent to 41. I take 100, and then the 137 to the 32nd power. I take the previous one. I square it. That gives me 81. So you notice that the cool thing about the binary exponentiation is that each part of the calculation you're only squaring the number before. So like computationally, it's pretty straightforward, and you never get numbers that are unmanageable with a calculator. As long as my number is not too big. But anyway, 81 squared is 6561, which is congruent to 61. So at this point, whenever you get back to the same number again, that means two different powers are congruent, and you can go from there. But I'm going to keep going this way. There's two different paths I could go down here. 128 power is congruent to 21, 256 power is congruent to 41. So there we go. I've got all my powers of 2 ranging from, the 8th power all the way up to the 256th power. And so we find, let me scooch this up here a bit, that 281, again, is 256 plus 16 plus 8 plus 1. So the 281st power I can break down as the product of the 256 power, the 16 power, the 18 power, and just a copy of 137. We proved that that was congruent to 41, that was congruent to 41, that was congruent to 21. And so multiplying these, well, first of all, I just dropped the 1 here because remember, working mod 100. So 137 is congruent to 37. And let's see here. Also, 41 times 41 was congruent to 81 in a previous part of the calculation here. See, I knew that from up here. 41 times 41 is 81 right there. Anyway, so yeah, 81 times 21 times 37, which happens to be 62,937, which is congruent to 37. So there you go. 137 to the 281st power is congruent to 37. All right. And the thing is, this example is relatively tame, but you see this method could be implemented without much more trouble to calculate something like the 27,651st power, right? You just have to do a few more squarings, but you could do it, right? So how would you have done that calculation before this? We sort of were just doing it with ad hoc methods, right? I mean, it varied the way I did these kind of calculations before, but this is a systematic method to do it, so it's kind of nice. So the alternate path is when you see two things match up, when you're doubling things. That means in this case that the 4th power is congruent to the 64th power of 137 mod 100, which means that the 60th power of 137 is congruent to 1. And so if I take my 281 and I divide by 60, division algorithm, I get 4 times 60 plus 41, which means that I can drop the 4 times, the 137 to the 60th to the 4th power. That's just congruent to 1, and I'm just left with 137 to the 41 power, but 41 is 32 plus 8 plus 1, so I can just do 137 times to the 32 times 137 to the 8th times 137, which is 81 times 21 times, it's congruent to 81 times 21 times 37, so we're right back to where we got to in like the next to last step in that purple calculation. So we again get 37. Again, math, it's very unfriendly. It doesn't allow for you to have your truth. It has its truth. Weird that way. Anyway, so here we go. Excuse me. So these are some notes that I wrote for abstract algebra a few years ago, and they're still relevant here, so I decided to put them into landscape and recycle them for your course because I think it's helpful. And all of this way of looking at the RSA encryption, I'll give credit where credit's due. I more or less got it from John Stillwell's Elements of Number Theory book. It's in there somewhere, but this is a nice book in its way, but it's not the right book for this course for sure. Anyway, so the RSA encryption scheme, it goes back to, RSNA are Rivest, Shamir, and Edelman in 1978. And apparently a couple of years before that, even in the early 70s, there's a British intelligence officer named Clifford Cox who more or less had the same idea. And if I had to guess, I would say that this idea existed elsewhere. I mean, it wouldn't be too surprising if more than these people had discovered this, and just the others weren't as successful in recording it in history. So, and I would say that this is somewhat related to like joke. If you've ever seen mathematical magicians who, ask an audience to give them, like a number, and then they do a sequence of operations to it, and then somehow they know the answer. It's not exactly that, but it's kind of like that. But anyway, as he says here, the idea of a trapdoor function goes to Diffie and Hillman around 76. So the trapdoor function is kind of something that's easy to fall through, but it's really hard to get back up through, right? Like it's kind of got an asymmetrical nature to it. So anyway, let me get to it here. So here's the RSA algorithm. And this is the, sort of the naive version of it. So first of all, you choose a pair. Trying to get it there. Choose a pair of large numbers. Let's call them P1 and P2, and we define n equals to P1, P2. Okay, so this could be stupidly large in real applications. Like we're talking about P1 and P2 are primes that are formed from hundreds of decimal digits. So when you multiply, and it's relatively, with a computer, it's relatively straightforward to multiply two numbers with hundreds of decimal digits, right? But what it's not practical to do in terms of computers, even today's computers, is to factor a number with hundreds of decimal digits into a product of primes. That is a computationally insurmountable goal for today's computers. Unless you just get lucky, pretty much, right? But it's very, very hard to discover P1 and P. It's very easy if I give you P1 and P2, then you can multiply them to get the n. But if I just give you n and then say, what is this a prime? What's its prime factorization? That is a very computationally troublesome problem. Anyway, here you go. So once you've figured out your n, all right, so not everybody knows P1 and P2, okay? These are not publicly known. You pick an e, also, that the Euler-Phi function of n and e is congruent, is relatively prime to e. Notice phi n you can calculate, right? Because, let's see here, what would phi n be? It would be phi of P1, P2, which would be phi of P1, phi of P2, right? They're primes. And so that's just P1 minus 1 times P2 minus 1. So it's not n, right? But it's also a really big number. And it's, straightforward to calculate that if you know the prime factorization of n. If you don't know the prime factorization of n, it is not at all straightforward to calculate phi of n, right? Okay, but we can publish e and n, so anyone can send you an encrypted message subject to the commonly held conventions. Let's explain what that means. Okay, so now this is the part I'm being very naive on, but basically your friend can take a message and use, say, the alphabet code, right? So you parse your message into four letter sequences. So you could trade the word cast for 03011920 because C is the third letter, A is the first letter, S is the 19th letter, T is the 20th letter in the usual enumeration of the alphabet, right? And so I say obviously there's more involved in real applications here, but I think you can use your imagination to see how we can trade words for symbols, words and symbols for a string of numbers within an appropriate scheme, right? Like you could use more than 0 to 26, right? If you're just using 0 to 26 to represent your numbers, you still got, you know, another, what, 70 plus numbers left over to encode other symbols, right? And you could even keep one of the later numbers as a sort of an error check, right? You can, if you ever study computer science, there's something called a parity bit. If you add another bit, you can check that your data has been transferred correctly. So all of that stuff can be worked into this, and probably needs to be worked into it for the proper complete RSA description, right? But anyway, so you take your message, you convert it to a number, right? And we'll just think about one letter just to keep the discussion simple here, right? But understand that, you know, that's part of the convention, is you got to decide how many letters you're going to take at a time. But anyway, let's focus on just one letter and see how we can scramble one letter, all right, using this what's called RSA encryption. So we'll call that one letter M, and we'll assume that M is less than N, all right, where N is the product of the prime. So M being less than N is not at all a large consideration for the real RSA encryption. So then what happens? Your friend, all right, your friend takes the N and the E that you published, and they run their message through the encryption map. The encryption map is simply to take M and raise it to the power E, all right, but that's all done modulo N, all right. So this is calculated mod N, all right. And so if you're calculating M to the E mod N, all right, so I should mention that. I think that's missing from this point here. That really should be included here. So this is another equals, equals, equals. And so this is done modulo N, right? This is done mod N, which means that we can do that calculate, use the binary exponentiation to do that, right, in an orderly way. So they calculate M to the E, they reduce it, mod N, and that scrambles the message M to the encrypted message, which we'll call F of M. And they communicate F of M to you without even hiding it. So anybody in the middle could intercept F of M, and it doesn't matter. Like, they can't undo it, because they, even though they know E, and they know M to the E, in order to undo it, they actually need to know, and they even know N. They know what you're, you know, they know you're working mod N. Doesn't matter. They can't undo the M to the E, all right? So even if the interceptor knows N and E, they can't just undo the message. So, but you know P1 and P2, you can calculate phi N, right? And you can find the multiplicative inverse of E mod phi N, all right? And by Euler's theorem, you know that, well, let's see here. Here's a calculation we can do. So remember, since M is, oh, curses. Well, let me shut up and just read the calculation here. So we find a D such that ED is congruent to 1 mod N, and then if we take our message and we raise it to the D power, we've got M to the 1 plus K phi N. But remember, Euler's theorem said that M to the phi N is just congruent to 1 mod N. And that was Euler's theorem. And so we just get back M again. In other words, raising to the D power undoes the raising to the E power. So we'll call D the decryption exponent, all right? Now, if you didn't follow the algorithm, that's fine. Let's look at an example that should clarify it, okay? So step number 1, all right? Step number 1, we'll for my toy example, we'll consider primes 13 and 17, all right? Very silly compared to real encryption, but there it is, 13 and 17. This gives us the product of 13 and 17 is 221. So if we calculate phi of 221, we get 192, all right? Because that's 12, you know, 13 minus 1 is 12, 17 minus 1 is 16, 12 times 16 is 192. So if we choose the exponentiation the encryption exponent as 37, that should work okay because that's relatively prime to 192, which means I'm going to be able to find that decryption exponent we need as described in part 6, right? Okay, so I use, now there's a little bit more to think, there's actually more to think about here in terms of choosing E, okay? Like this sort of choice of E without attention to the structure of the group of units is dangerous. I will explain at the end of this lecture why that is, from my own personal experience. But anyway, so we choose an encryption exponent as 37. My public key, so then I communicate. My public key is 221. My encryption exponent is 37. Then your friend chooses a single letter message of J. And J happens to be the 10th letter in the alphabet, so that gives us the, the naive code of 10. My J is 10 in disguise, all right. Anyway, so then your friend takes the message and raises it to the encryption exponent, 37. So 10 to the 37 mod 221. All right. Now, there are various tricks to actually perform this calculation, but we'll use the binary exponentiation. So 37 is 32 plus 4 plus 1. So I calculate 10 squared, that's 100. 100 doesn't reduce mod 221, right? And then I take 10 to the 4th and I square it. That gives me 55, congruent to 55. 10 to the 8th is congruent to 152. 10 to the 16th is congruent to 120. 10 to the 32nd is congruent to 35. So each one of these I'm splitting off a multiple of 221 to find the least residue, right? The remainder upon division by 221, respectively 152, 121, 35 for these, yeah. Anyway, so there you have it. I've calculated my binary powers. And then putting it all together, 10 to the 37 is 10 to the 32 times 10 to the 4th times 10 to the 1, which is congruent to 35 times 55 times 10, which is 19,250, which is 87 times 221 plus 23. I used a calculator, obviously, right? And that's congruent to 23. So, my encrypted message. And you see here, sometimes I'm being a stickler for writing the equals, equals, equals. Sometimes I'm writing equals. Let it be understood that this is all done, what? Mod 221, right? I get tired of writing mod 221 at various points, so my apologies. But now, moving to step 6, I need to calculate the decryption key, right? This is not done publicly, right? This is just for me. And so here's how you do it. I want to find the inverse of E in Z192, so we can use the vector Euclidean algorithm, right? Step 1, 192, 37 AB, and then I can subtract 5 copies of 37 off 197, leaves me a remainder of 7. Then 7, I can let's see here. I can then put, let's see here, 5 copies of 37. That's funny, 5 again. So I can put 5 copies of 7 into 37, so remainder is 2. So that gives me this. And then finally, I can put 3 2s into 7, leaves me remainder 1. Remainder 1, we're done. And so we get 1 is equal to all this stuff here, right? But that simplifies to 16a minus 83b, which is to say 1 is equal to 16 times 192 minus 83 times 37, which shows me that in Z192 the inverse of 37 is minus 83, which if you add 192 you get 109, all right, in Z192. So my decryption exponent is 109, and so 109 is 64 plus 32 plus 8 plus 4 plus 1, right? And so what do? I do the binary exponentiation trick again, right? I take my encrypted message of 23 and I raise it to the power 4, 8, and 16, work out congruent to 55, 152, 120. And then, continuing, I take the 32nd power and the 64th power, I get congruent to 35 and 120 respectively. Hence, mod 221, we have 23 to the 109 power is the product of 23 to 64, 23 to the 32, 23 to the 8th, 23 to the 4th, and 23 itself, which is congruent to 120, 35, 1 times 152 times 55 times 23. And then what I did was I just multiplied a few of these to get 4,200 and a few of the other ones to get 192,280. And then to get from here to there, sorry, I left my calculator in the other room, otherwise I'd show you, but I'm pretty sure what I did to get from here to here was just divide these by 221, subtract off the integer part, and multiply by 221 to find the remainder. So I just used a calculator to find the remainder upon division by 221 in both of these steps. And lo and behold, back to 10, right? So I don't know if this is probably, I mean, this is not convincing, obviously, because you can take 221 and you can factor it into 13 times 7, right? So this is by no means secure unless you're working with grade school children who can't find the prime factorization of numbers. So I guess in a typical population, this is actually very secure. But sorry, let us not revel in the poor teaching of children, I suppose. But the point here is, though, it's really surprising, I think, when you first understand this method, that it's like it seems so bold. Like you're just telling people, yeah, you take two numbers, you multiply them together, you get this, right? And so basically it's like this taunt to the world that you can't factor those, haha. And yet you know how you multiplied them, so you can unmultiply them, right? But everybody else can't, because it's really hard to factor large numbers. But not impossible either, right? Which is why encryption can be broken, this kind of encryption, given sufficient time and computational resources. Like there are techniques, right? So maybe you start to understand some of the games you could play here. And the interesting thing, right? I think a bit of history is very funny. Like, in the early 19th century, there were some of these, rather highbrow ivory tower number theory types who took great joy in the fact that their mathematics, not like those applied mathematicians who study differential equations or ugly, calculus or whatever else that's, so clearly engineering real world applications and all that. This is number theory. This has no application to the real world. It's just, it's pure mathematics. The great irony that kind of that kind of mathematics has probably more application to the real world than almost anything else out there at the moment. Every email you send, every bank transaction that you make online, all of that stuff, in one way or another, is built off the back of this. This is why you can transmit that information in an encrypted way. That's right out in the open. The information's there. People can intercept it midway, and yet they can't unwrap it, right? On the other hand, this is also can be used against you as well, right? When somebody hacks your computer and they encrypt your hard drive and then demand, if you're a hospital or something, $50,000 to unencrypt, to get your data back. You're kind of stuck. Like, you can't undo it. It's just, it's messed up. Now, this is, of course, a well-known procedure, this trapdoor function idea that I've described here, the exponentiation and decryption. But there are other methods of encryption using what are called elliptic curves. Elliptic curve cryptography is much more cutting edge. There's a group that's corresponding to an elliptic curve. And just like that really made this work here was the group theory of the group of units, which is pretty simple. So if you used a more complicated group to somehow run the encryption, you can see how this would not be as easy to unravel, sort of heuristically. But Anyway, one last thing. So the first time I taught number theory back in, I think it was like 2015, I figured this thing out for the first time because I never really cared about encryption before I taught the course. And I thought, okay, well, I'm going to use this mod 221, right? And I calculated it. I got 192, and I thought, oh, okay, I'll use 49. 49 is clearly relatively prime to 192, right? And the thing is, this was a really unfortunate choice because you can calculate the group exponent of the group of units mod 221, and the group exponent is actually the least common multiple of 12 and 16, which I believe is 48. So what happens when you calculate the 49th power of something in this group of units? Anything to the 49th power is that thing again. So if you're trying to scramble a message, raising to the 49th power mod 221, it's a very bad choice because it doesn't scramble at all. So I had this class in number theory. I gave them the n, I gave them the e, and then I said, all right, you guys, you pick a message and you encrypt it, and then I'll come back and I'll come back and then no, I think I told them the number. I can't remember. I think I told them the message to encrypt, and then I left the room to let them do it. And I came back, and they gave me that they told me that their m and their scrambled m were the same, and I was like, and so it was a waste of 10 minutes of class, and then I was like, oh, it has happened to me. But so the long story short is when you're choosing E, you do need to be wary of the group exponent of the group of units, because if you choose your E to be too close to the group exponent, you might not scramble it at all, or your scrambling might be not really very good. But anyway, there are hidden dangers, and this, of course, is just a naive presentation of it. But anyway, I hope you enjoyed. Thanks.